information in the given settings. So along with this, we try to explore something called as a form and frequencies. So in the form and frequencies are the ones which are treated to be a resident frequencies of the oral cavity. So oral cavity means like the mouth region where the mouth region where these are these frequencies are resonated. I mean to say, so the from the vocal cords, like if you observe from your vocal tract, so the vocal folds will try to vibrate it, and from the vibrations your oral cavity means like from your mouth, palate, lips, uh, and the movement of your tongue will everything will matter, so that this will the shape of the lips will be a major component in understand in creating the resonant frequencies of your sounds. So here we have understanding that the fundamental frequencies and the formal frequencies are having an impact with the speaker height and age. So we try to explore different formant frequencies, like formant 1, formant 2, and formant 3, and so on. So there we tried looking at these spectrums, and observe that the and we had look at the difference of fundamental frequencies, and along with the other form and frequencies, that we could see that there is a correlation with height estimation along for the form and frequencies and the fundamental frequencies as well. So then we also looked at the harmonic features. So the harmonic features are the resultants of your vocal fold vibrations during the voice speech. So for example, I mean, just like to understand from your side itself, if you place your thumb or any finger for example, on your throat, you could see like when you call a vowel, for example, like a, e, u, like all the vowels. So you could see the vibrations happening at your at your throat. So I mean, throat is a very broader term, like you could say like the vocal tract. Okay, so if you try to take any consonants, then you could not have that much vibration. I mean, you could not see the vibrations there. So here we also observed, and the literature is also identified that the harmonics are also having a cues related to the height and age of a person. So here we looked at the spectrogram and the spectrum corresponding to the right side here. So here this spectrogram is talking that timid SA2 sentence, where is two speakers. The top one is the shorter speaker, and the bottom one was the taller speaker, like where we could see that the spectrum representation, these are the harmonics which are a spacing of 230 hertz. So if you observe these spectrum spacings here, the width of the peaks are wider for a shorter speaker, and when compared to the taller speaker, the width is shorter. So you could see that there is only 160 hertz like spacing between these spectrum, these peaks. So otherwise, if you can see from the spectrogram level, I have zoomed it here. So if you can observe, the spacing between these two, basically these spacings are equivalent representations here, what I have shown as a spectrum. Okay, so this spectrum, these spacings are wider for a shorter speaker, and these spacings are thinner when it comes to the taller speaker. This was the observations which we could identify from the harmonics itself. So we could understand from this, like these features are represented at the overall utterance level, not at the phoneme level. Okay, so now when we look at these features, so how we could see like uh, these features are impacting the overall performance. So to have this understanding, we looked at the TB data set where we have where we have like 230 speakers in that 630 speakers in that, like a like we have like a 460 speakers are for training, and around 170 speakers for testing. So here each speaker have been contributed like a 10 utterances, and in that two utterances are been same, and this particular data set is having a height and age details only. Of course it is having a text details, so but in our context we are not looking at the text context, but we are only looking at the utterance plus, sorry, audio plus height and age details. So to have a error measuring metric, so we have used the mean absolute error and the root mean square error as the error metrics. So when we try to say like we are looking at the error metrics, or when we are looking at like how the system is performing in our case, so we need to have some kind of a like I would say like a benchmarking something. So in this case what we try to use is like we try to understand something called as a target mean predictor. So target mean predictor is something like we won't be looking at about the features, what we won't even look at the audio, we directly look at the mean which is obtained from the training data. For example, from this one 460 speakers, it will be having a some mean of it for a height and for some mean for the age. So we will try to use the height and age of the training speakers to test on the test speakers. So I mean to say, for example, this trained speaker is having a 170 centimeters as a mean, sorry, 160 centimeters as a mean age, sorry, mean height. And for the test speakers, if you see like 170 is my 165 is my the height of a person, so then the difference is equal to 5 centimeters. Then for that difference we are computing the mean absolute error and the roots mean square error. So here we don't even look at the audio, we directly look at the statistics of the particular uh, speaker and the data set. So this makes the benchmarking such that like if the particular value if the error is less than this target mean predictor, then only we could say that the the, the model which we have showcasing is better. Otherwise whatever we are showcasing up was of same like not at the remarkable level. Okay, so as I just mentioned, so we have just a sec, I just want to view as a full screen. So here, when you look at, in this case, as I just mentioned, we with the target mean predictor TMP here, we worked with the first order statistics, formants, and harmonics, and harmonic formant locations as well. And here we looked at instead of looking at both male and female speakers together, we try to separate them as the male speakers and the female speakers, and then we try to identify how these features having an impact on the overall performance. So we could see that we could able to identify some details from the female heights of using formants and first order statistics, and here the harmonics as well, in where we could see for the height and age estimations. So that now what we try to do is like we try to perform the simple average across the regression outputs from all the three different features like a font, capsule coefficient, first order statistics, harmonics, and formants. So this three feature combination has helped us to have the performance which is less than the state of which is beating the state of art results in terms of female speakers and the overall male and female speakers. And we are par with the state of art. It's been only 0.1 year less when it comes to the RMSE for height estimation. In the similar case, when it goes to the age estimation, it's all about again three feature combinations are working better for this particular height and age estimation. So we try to dwell more into it understanding how this particular error is like which band of speakers are more compensating this error, this much error. So we have looked at like a six different bins, like from 145 height, 145 centimeters of height to 203 height. These are the minimum and maximum range of the speakers. So in this we observe that we have like the speakers from 150 to 160 centimeters height are very less, and we have from 190 to 203 centimeters as 32 speakers. So if you look at the band which is like a 4 and 5 is having a more number of speakers, and we could observe that the test prediction error, or mean absolute error, and the RMSE error is very less when compared with the outliers here. So these outliers are contributing more in terms of overall performance of your data, overall performance of your system. So it is evident that when we have more number of data, the model can represent these presentations very clearly than the one which have been trained with the very less representations. So here also we could see the same trend for the female speakers as well. So this is for the height prediction. So then we look at the age prediction as well. So we, as the TB dataset, have a range of from 20 years to 76 years. So if you observe that after 45, after 40 years, so these are very less represented. And when it comes to the band like a 20 to 25 years, 20 to 30 years, so there are more number of speakers, and so you could see like the error contributed at this point are very less, and it could be, if you look at the other bands, it's a 10 times folded of your mean absolute error and the RMS error. So now with this understanding, what we try to look at is, so how, whether we could able to predict the same error patterns, whether how, if it is from the full 5 to 10 seconds of a speech data, or if I cut down the speech by 2.5 seconds, 2 seconds, 1.5 seconds, 1 second, and zero point 0.5 seconds, how it is varied. So this is like again the same representation for a male and female separately. So if I look at both the male and female together, so if you could see that with the minimum of 1 second of, or like 1 to 2 seconds of a speech data itself, we could able to identify the mean absolute error as equivalent as like minimal error, so by 1 to 2 seconds of speech data itself. So you can see very clearly in terms of from 1.5 to 2 and 2 to 2.5, there is no big changes happening in this context. So that's where we could say, like, with the minimum amount of 1 to 2 seconds of a speech data, we could able to identify the height and age of a speaker. So this is not the end of the story, right? So we try to look at, so far we addressed with the only monolingual context. So now we need to do the same robust analysis for multilingual and multi-accent settings as well. So, and also we need to extend the same settings with the other physical parameters like a shoulder size, waist size, and the weight of a speaker. So for this context, what I have tried is, like, I have collected two different data sets. One is called as audio forensics data set and NISP data set. So this AFDS data set is having like 200 speakers, and NISP data set is having around 350 speakers. So here, this is the AFDS data set is a pilot data set. I would say, like, here we have targeted like a different native speakers, like a 12 Indian languages, and the maximum speakers are from Hindi, and per native language the average is about 17 speakers. So that's the with the pilot data set, which is AFDS. And when it comes to the NISP data set, rather than diversifying our speakers, so we concentrated only on the five Indian languages along with the English. I mean, of course, the AFDS is also having the Indian speech as well, Indian English speech as well. And here every language we made a minimum of 60 speakers to be speaking, and being at the Hindi as a language, we have collected around 100 speakers here from each language. So here we have both Hindi and English from each recorded from each speaker. I just want to mention here, what we have recorded is not a conversational speech. We have given a set of paper instructions to read the particular audio, sorry, particular text. So we have recorded. So it is to be a read speech. So, as part of a data collection, so we have looked at the native language, like which is like the usual language which people are more convenient, which L1 is treated to be their mother tongue. So, we have given the text to read them in their L1 language, and also the second language as a L2, which is a English script. So, we have collected the details like geographical location, from where he belongs to, and the other physical parameters just like as mentioned, so height, weight, shoulder size, waist size, as well as age and gender. So so this is more in details about what are the languages which we have collected for AFDS, and how many male speakers and female speakers. In total, we could say that we have around 17 hours of a data from AFDS dataset, and then we have like around 56 hours of data from the NISP dataset. For your better reach, I would say like this NISP dataset have been publicly made available in with this link which I have given in my slides. So if you feel free, you can contact me to download it, or otherwise it's anyway I made it publicly available, so you can directly reach to search for the NISP dataset. You can able to locate it from the GitHub itself. Then, so this is like just a pictorial representation from where and all we have collected in more number of speakers from the across parts of a different parts of India, both NISP and the AFDS data sets. So, as we need to do the experiments on the multilingual setting and multi-accent setting, so what we have done is like we have represented the same set of speakers in whatever we have tried, like first order statistics using ML filter bank features, harmonics features, and the harmonic features. So then what we observed is uh, here one thing we have tried something unique is like being this data set is with a limited number of speakers, so we tried to use the Timit UVM for computing the first order statistics on this particular data set. So that helped us in trying to achieving the better numbers. So here this is the combinational feature observations what we have found out when compared with our target mean predictor. So here we could see that the combination of three features have been much more much more differentiating the target mean predictor and the result. So it means to say that whatever we have tried was not a fluke, but it is have some substantial correlation with the height, weight, shoulder size, weight, and age of a speaker. So we also perform the same duration analysis, being this particular data set is not of restricted time duration, because we collect the AFDS data set have been collected like the maximum duration of the particular the audio is like a 2 minutes. So it's like a continuous stretch of an audio. When it comes to the NISP dataset, we chopped the audio, not like chopped, like we recorded directly like a different sentences. So each sentence is been appearing on the screen, so that the speaker would be reading aloud in front of a microphone. So that the length of the each speech again varies from 5 to 10 seconds as well. But now with this duration analysis, we could identify that with a minimum of 2 seconds of speech data, we could able to identify these details, which is similar to the full length of the speech data. So now so far we observed is all about the utterance level and how these and all those and all we multilingual settings, right? So now we'll try to multi-accent settings. So now we'll try to look at the lingual settings as well. So what we try to observe here is we try to understand much more in details. Like we train the model using the here the matched condition is something like we train the model in the either English or the native language, and the test is also testing the data is also with the same native language and the English. So in the mismatched condition, what we have tried is like we trained the model in English and tested with the native language, and we trained the model in the native language and we tested in the English language respectively. So here also we could see that even with the matched and mismatched conditions, so what we have observed is the difference of in the um, physical parameter estimation is not that heavily charged, but the change is very minimal here. So with this understanding, we could say that the model which we have showcased and which we have trained was robust to the language as well. So yes, now we try to perform the same with the NASP dataset as well, like the same settings what we have showcased just now for the AFDS dataset. We tried doing the same with NASP dataset as well. So here we could see that the height and age, height, shoulder size, weight, and age of the speakers are better with the um, mean absolute errors with the three feature combination as well. So here one observation what we have seen in this context is the waste was not having a very much impact with the physical parameter estimation using the speech, so we discarded with the NASP dataset. So the same we have looked at with the effect of language as for height, shoulder, and weight and age estimation using the NASP dataset for matched and a mismatched condition for the understanding the effect of language. Now, in short, what we have tried is we have created two data sets, like two multilingual data sets, and we proposed the combination of features is performing better than the TMP in multilingual and multi-accent settings. And with the 2 seconds of the speech data, we could able to get the system performance as equal as similar to the full length of the speech data. So, and the model is robust to the language. At the max, there is a 2% to 3% degradation with the AFDS datasets and 9% degradation with the NSP dataset. So far we looked at only the conventional methods. Now let's try to understand something with the end-to-end architecture. So in this end-to-end architectures, what we have tried something new is we have integrated this joint prediction. Like we have so far in the conventional settings, what we tried is we have looked at the we trained the model for height separately, we trained the model for age separately. Now in this joint architecture, in this joint prediction architecture, what we have tried is we try to predict both height and age all together at a single go. So, and also any neural network, we have proposed a very novel scheme of installation using the support vector regression parameters, which helps us in limiting the large amounts of data for training purposes. So let's try to understand the uh, DNN architecture which we have developed for predicting the physical parameter. Here, what we tried is we have divided this particular architecture into three different parts. In that, part one and part three are my trainable parameter, are trainable layers, and part two is of like frozen layer kind of. So here in the first part, what we tried is like we have computed the first posterior probabilities from the MFCC features which we have obtained. So in our context of initially we have computed the first order statistics. That was our my first representation, feature representation, right? So we were trying to represent the same replica of the first order statistics from the raw audio itself. Sorry, from the MFCC feature. So what we tried is instead of doing that first order statistics training separately, we tried to do this representation using the neural network architecture. For that, we tried to feed the MFCC features, that feature as a from the input layer, and here we initialize this layer with the means of trained model from the GMM UBM. So then we we propagated with 256 components, like 256 neurons here, and then we taken out the same 256 interpolated to 512, and again decimated to 256 256 neurons here. So this particular layer is the part of our training model, training parameters. So once we have these 256 neurons, what we tried is like we multiplied the MFCC features with this 256 neurons, and which is kind of equivalent for our first order statistics. We that is with the across every frame. So what we have tried is like we average across all the frames, so that we'll get the 256 means from from all the frames of each utterance. So for one utterance you could have 60 cross 256 representations, and that is flattened, so that this flattened vector is given to a dense layer to predict the height and age of a speaker. So here also we tried doing something more interesting. What we have tried is like we trained the model separately, which we have done the support vector regression model, and we have used their weights here and assigned those weights at this point, so to this layer, so that it can give the better biases. So here we what in total what we have eliminated here is, so we with the help of initializing the GMM UBM weights, we have eliminated the model training for a like large amount of speakers, and which helped in reducing the computational time as well as the need for like large amounts of speakers data. So yeah, this is a part of it. And then these are the results corresponding to the timid data set, which we have explored now. So the as I said, like a default predictor, which is our TMP, and the GMM UBMS supported regression model, and our this current DNN model. So we could observe that this current DNN model is performing better with the height and with the age, and par with the height estimation. So they besides with the timid data sets, we observed for the duration analysis as well. So as just mentioned in the previous slides, we have observed that from 2 seconds of speech data itself, the DNN model is performing better, like as equal as the full length of the speech data. So then the same set of experiments we try to explore with the NISP dataset and the AFDS dataset, so that we could see that like long story in short, like everything these parameters whatever we have explored for the NISP dataset and AFDS datasets were performing better with the proposed DNN architecture as well. So in short, I would say like we have like explored different like we have proposed a new architecture for identifying the for estimating the multiple physical parameters by introducing a novel initializing scheme. And we observed that with the 2 seconds of speech data itself, we could able to observe the performance which is similar to the full length of the speech data. So these are the takeaways from this particular research work which we have considered. So here using the timid data sets, where we have explored 3 different types of features, so which are like MFCC features, harmonics, and formants, and we have made that the system is independent of the transcriptional information, because we looked the model at the utterance level, and also we showcase that these representations are robust with the short durations of the speech data as well. And then we have collected the 2 different data sets, which is multilingual and multi-accent settings. So and also we observe the same model is robust to the speech, so robust to the language along with the short duration of the speech data. And also we benchmarked these new data sets, these 3 data sets along with the 2 collected data sets with the deep neural architecture, and also this system is robust to the short duration of speech data. So these are the couple of references which I have encountered during this research. So thank you. this is the this is a part of speaker profiling, I would say. But if you allow me to talk something more interesting in terms of motivational interviewing, which is a part of, again, a kind of as profiling itself using a speech. So uh, or should we have a questions at this point, and then we'll go to the next talk, next part of the talk. So I'm happy to take the questions if you have, or else I can go ahead with the next
Is
topic
anyone
which I would
having
like.
any questions? You can unmute yourself. You can ask, or else Sarif sir will go to the next session. I don't think so. So if anyone wants take this work ahead, you can contact to Sarif sir directly, so that he can provide the data set and all other help. Okay, sir.
Sure.
Next, move to the next.
So what I would like to showcase here is something called as motivational interviewing. So here, let me try to make you more understandable. Like, what is motivational interviewing? So motivational interviewing means like it's a client-centered approach that aim to resolve the ambivalence and encouraging the behavioral change. I mean to say, here in this conversation, I have a therapist and I have a patient. So in this, one of the patient would be explaining his problem, and the therapist would like to listen all his problems or whatever he mentioned as a problem to him, and the therapist will try to give a possible solution or try to understand his behavior, so that he could able to say something positively to overcome whatever the behavior the client has. So he will try to help the client to change the mindset, or change the like try to resolve his confusion, and try to encourage him or her for a particular change in his or her behavior. So this would be actually more concentrated with the client's behavior. So basically, uh, the therapist try to motivate the client to get more uh, changes happening to himself. So originally, this motivation interviewing was used or developed for substance misuse. So substance misuse means like a drug addict, or like something like alcohol addict, or some XYZ reasons. Okay, so this makes that there is a physiological changes happening to physiological and the physical health changes would be expected in his behaviors. So we tried by using this motivation interviewing therapy, people are trying to understand and give a solutions to him or her, and try to change his lifestyle habits, and like try to change the in terms of addictions and gambling. So in understanding it, like this is motivation doing promotes the change talk by encouraging the client's willingness to change his behavior through the dialogue. So in understanding the client behavior, the motivation interviewing skill code have categorized into three major categories, which is like a kind of a change talk or sustain talk or the follow neutral. So in this context, change talk means whenever I am discussing my problem with the therapist, so if the therapist say like, no, if you should not, for example, if I say like I am like an obese guy, so if people say like the therapist say like you are like too much obese, if you can start doing some sort of exercises or cut down your junk food, so you could able to maintain your physique as well as your health condition will improve. So this the motivates the me to get to not to have the junk food, or go for a walk, or go for some sort of exercise activities and all. So the moment I say like yes, this is good, like I want to change from today, or I will go for I will go for a walk, I will go for exercise, I'll cut down my junk food, like this kind of positive represent positive behavior, we are changing his behavior instead to be your change talk. Or else if that particular guy is like, why should I do it, so if he shows any reluctance in doing it, so or he is maintained, he would like to do the same behavior, like why should I, so in that sense we call it as a sustained talk. So, or otherwise, if even after understanding the difficulties and the pros and cons, but still, if the person is not willing to, is not giving any proper acknowledgement, just like a show any kind of changing behavior or like a reluctance, then that kind of a sentence is treated to be your follow neutral sentences. So here, so literature we have explored. Actually, I was also a part of this work in Nakano Sensei lab, but unfortunately, I was not much involved there. But later work I have been involved in this context. So what we have explored is mm, uh, with the help of language information and the facial cues. Okay, I'm sorry if I forgot to mention, so the work which I have carried out here is all about the food habits by food habit changes in the from the Japanese speakers. So this data set have been collected via Zoom meetings in the COVID time. So we have access of the facial information as well as the audio informations together. So the from the facial informations and the language informations, we could able to identify the change of behavior from the speech itself, sorry, from the persons. So this have a little hiccup here. So once we see that the particular facial information and the language information are side by side, we could able to identify the, or we could able to see identify the speaker. Basically, if you observe that revealing the data, for example, if it is a small, I mean, the food habitual change was not that imminent, but if it goes with the some um, other addictions, so then people are not that comfortable in revealing their physical identity. So that time it is not the recommendable work. So what we have tried is like using the language information and the speech information without taking the facial information. So this has a much more impact with the current research. Like instead of going with the language and facial cues, we have looked at the language plus speech cues itself, so that the identifying the person is not that directly impacted as the previous case. So uh, yeah, so this has some much impact with the and less sensitive and more easily collectible alternative for the for this work. So as I just mentioned, this is a part of Japanese data set. So here we have 4 counselors and 57 clients, and each session will go for like approx 20 to 22 minutes. And we have each counselor can have sit for the 12 to 13 sessions, and total out of 57 sessions, like we have taken only 48 sessions because of some technical issues. We have discarded the remaining sessions. So here we have generated the what I say, like generated the transcript for the as a part of language information using a Japanese Google ASR for the language information. And we have extracted the language features such as like using the Hugging Face model, and we extracted about 768 dimensional robot vectors as a for each token as a sorry each utterance as a token. And then for in terms of speech representations, we have extracted using OpenSmile features. And there we have looked around the features like fundamental frequency, zero crossing rate, MFCCs, and root mean square errors are having more and more understanding here with the feature extraction part, like with this motivational drawing. And we tried this model with using the BiLSTM models for and other than looking at the three different classifier, three different classes, we try to identify that change stock or the non-change stock. So in the non-change stock, we have provided with the follow neutral as well as the sustain torque as well. So this is the architecture which we have trained for classifying the change stock and the non-change stock. So as I just mentioned, we have extracted the Robota embeddings of 768, and we have provided the speaker ID, and we given with the BiLSTM model. So similarly here we extracted the speech features for the using OpenSmile features, and we added one extra feature which is like 360 384 features here, and we added one extra feature as my audio feature, which is normalized duration as extra feature. Okay, and also we gave a speaker ID as well, like whether he's a client or the therapist. That details also we gave as part of the um, as part of binary value as a 0 or 1 as a part of the feature vector. So these have been again given with the BiLSTM model. So at the end, from the fully connected layer to the classifier, we have tried to identify the binary classes, like whether it's change stock or the follow neutral, sustain torque or the follow neutral. So we could see that with this setting, we have are on par with the language and facial model. So here we could see that the precision and recalls are almost kind of equal, and lesser than the language and facial model. So with this understanding, we could say that the language and the speech information itself is sufficient. I mean, self-sufficient, I would say, like for identifying the change stock, I mean, behavioral change of the speaker. So I would say like a change stock or the non-change stock. So here, just to be much clear with what is something called as a lang plus yes, lang plus SWT, SWR, SWT plus SWR, as duration, what it means is like here, yeah, language yes means I would say like language plus speech only. So then what we tried is language, we have SWT. So here we have so if you look at the model here, we have weighted. So we have weighted the each vector, each feature vector with the duration of the speech. So that is said to be your weighted speech. Okay. So here that would be STWR, and then what the next one is SDUR. So here now I just taken the speech vector, and also we gave the just the sorry, normalized speech as a vector, sorry, one unit. So that would be given as my one more feature. So that will be lang plus um, duration as my one of the feature. So now at the end, what we tried is like a language plus the weighting of your weighting with the duration, and the duration as a feature. So all these three combinations have, again, is provided for the model. So this gave us the best combination for identifying the change stock and the non-change stock. So yeah. So at the end, as a conclusion, I would say that the multilingual approach for the proposed for detecting the change stock and the non-change stock by using the language and the speech representation from the motivational sessions on diet and physical activity on the Japanese data set was doable. And then we achieved these results as far as the language and the facial models. So we are actually we would like to enhance this particular task in terms of more understanding the counselor and client behaviors of more in my dialogue generation. Yeah. Yeah, thank you so much. Thank you for your attention, and I would be happy to take any questions in this or the previous talk as well, or previous part of the talk as well. So thank you, sir. So so Um, Hello, sir. Ranjan, sir. Hello. Hello. I would be happy if I can able to take any questions here. Is there any questions in the chat? Okay, no questions. Satyananda, thank you, sir. Sir, is there any questions to be addressed?
Yes, any questions? You can unmute. Participant, you can unmute. Yes, any question? African students can ask some questions. Sir, we have so many foreign students are there in our university, like from
Oh,
African continent, and many have joined. Faculty and students also have joined in this, means, registered in this workshop. So don't
oh,
know
that's
whether
great.
they have joined today or not. So
Okay.
let us see if you can collect some data set, new data set by the students, and from the students, if you can collect some the indigenous data set or like that, then see you can formulate some problem statement.
Sure, sir.
Okay, so I will share this. You just share me the PPT, and the first PPT I will share to the students. And they
Sure,
have
sir.
thank you, sir.
Thank you, sir. So, can I leave?
Yes, yes, sir. Thank you very much, sir.
Thank you very much, sir.